All right. Uh, why don't we begin? So today's speaker is Endawoke Yizengaw, and he was born in northwestern Ethiopia, known as Amber. He received his Bachelor of Science degree in Applied Physics from Addis Ababa University in Ethiopia, and then his Master of Science in Atmospheric Science from Tromsø University in Norway. And then he did his PhD degree in space science at La Trobe University in Australia, graduating in 2004. And then he spent 2 years as a postdoctoral researcher at UCLA, and from 2004 to 2006, where he received the Chancellor's Award for Best Postdoctoral Researcher. Then he was a research scientist at UCLA from 2006 to 2009 before moving to Boston College as a senior research scientist, where he has been ever since. And he has been a principal or co-investigator in several interdisciplinary projects, primarily focused on deploying ground-based instruments, including the AMBER project that comprises of 13 magnetometers deployed around the world. He is an author or co-author of over 70 peer-reviewed publications, and he's received numerous awards, including the 2009 UN IHY Award for the Best Creative Vision and Outstanding Leadership, and very recently he won the 2018 AGU Joan Simpson Medal for his significant contributions to the Earth and space sciences as an outstanding mid-career scientist. His research interests include space weather, magnetosphere, ionosphere coupling, equatorial ionosphere electrodynamics, and ground and space-based GPS tomography. And today he will present his work on longitude and seasonal variability of ionosphere disturbances.
All right. Thank you, Nick, for that introduction. Actually, Nick made a history because I never been in Boulder throughout this year. So he made history by inviting me for the first time to be in Boulder, and I really appreciate that one. Thank you. So I'm going to talk about the longitudinal and seasonal variability of ionospheric disturbance. When I say ionospheric disturbance, all mid-latitude and low latitude as well. So before I show you my outline, I just wanted to ask a question. As astronomy scientists, what are we trying to do? That's all the time. Every regular people will ask you this question. When you say, I'm a scientist, and what science? This space science. What do you do for that? What are you trying to address? So I just wanted to have a cartoon that I wanted to show you. This is just to solve the unknown problem of the ionosphere. That's our objective as astronomy scientists. So way before 20 years before that, there was a saying that if you understand the forcing from above coming from the sun, then you solve everything. And then later on, maybe a little bit earlier than 2000 or around that time, they recognized that no, it is not only that part, there is also forcing from the bottom. So if you combine these two, we probably try to understand. I have an analog just for fun. Just a politician also to have to make a country prosperous and really peaceful, operating a government. There is one thing that they need to consider. I mean, if you only just include in the government the ideology of one party, then there will be a mess, including government shutdown. So you have to include everybody, so from other parties, just like forcing from below. And then you get a smooth transition or operating government. So there is 5 steps that you need to apply, but it's not for the government that I wanted to point out here, just for the scientist. So you have to define a problem and what try to address, and then don't discriminate anybody. Oh, he's ionosphere, he's magnetosphere, he's solar. Include everybody together and ask them what they can contribute. And then engage everybody into different problems and then evaluate the result. If it doesn't work, go back to that point and do the same thing. So that's how we can understand physics behind the ionosphere. And once we understand the physics, then Hanlin will be very happy to model it. So here is the outline. So the mid-latitude ionosphere irregularity, that the reason our team just get selected as a NASA Living with a Star Institute, just to address the mid-latitude ionospheric irregularity. You may wonder, the mid-latitude is very quiet and nothing will happen. And then the next topic that I'm going to touch down is the longitudinal variability of equatorial irregularity. And recently, my team is just working on this, the forcing from below, if that is really the one which is controlling the longitudinal variability as well. And then I'll talk about the variability of equatorial electric field, at least for the day side. And if time allows, I will show you what is the future really coming up, living with a star mission like ICON, GOLD, and GDC. And I will talk about this one at the end, if I'm nice and have more time about it, what we did for international stuff. Here's a mid-latitude, way before in 2002. And here is just the 4 satellites over there. That's TEC at the bottom here. And then this is the dashed line is a quiet time. And here is the equivalent S4 index, the irregularity. And these are 4 satellites, and then measured in at Cornell University, which is located over here. And here is the track of the satellite. 4 of them. There's 2 satellites over here, and the other one color-coded, but in grayscale with the S4 index. You can see the S4 even at mid-latitude in a very regular, it's not that big a storm during 25 to 26. It's a reasonable storm, but you get really S4 index close to 1 sometimes at mid-latitude. And the question you ask is, what is the physics behind the mid-latitude? We know the low latitude, the coordination is different, everything. But what is going on at mid-latitude that, and this is because of this funny structure that we quite often we observe. This is the latitude as a function of longitude. The color is TEC, total electron content, and you can see a really sharp gradient of density up there and the mid-latitude region. And we observe this kind of stuff quite often. And I mean, I put sometimes, actually many times, different instruments just to demonstrate if this different instrument actually observe the same structure. You can see the plume, seed plume over here, and the DMSP satellite is crossing that, and you can see how the density is pushing up. Here is the topics altimeter TEC, and then when the sharp gradient happens, and the TEC goes down from about 20-something to 5 TEC unit in 1 point. So that is the reason why we have the high latitude irregularity. I'll come back to that point. And then, as I said at the beginning, you just combine, whether we like it or not, they are actually interconnected. This is a plasmasphere, which is taken by 3 cameras at the image satellite. And the brightness is the helium brightness, and you can see this plume structure, and these white squares are the plasma pose position. So if you map that one into the ionosphere, they are actually this mid-latitude, I mean, the plasma pose positions are actually way aligned with this trough structure where the density gradient happens. This white triangle is actually the plasma pose position extracted from the plasma pose. Now, how did that happen? Why this kind of structure we have quite often? There are two ideas here. I know there was a workshop to address which one is correct, but I'll show you what we believe in it. There's 2 ways. One is the density redistribution from the low latitude region. And that's how you get that. And the other one, which is a Utah State and UT Dallas and the others, no, it is not connected with a low latitude density, but it is actually the density enhancement at mid-latitude, and then of course underneath, you get that kind of plume structure. But now we have measurement. So here is the first one is when I say redistribution, you just have the E-cross-P drift at the bottom. You push the plasma up, and that plasma is actually, due to the gravity and the pressure gradient, slip along the magnetic field line. And then you have this electric field coming from the magnetosphere, which is called SUPS electric field. That takes it away to outside the plasma pores. And then at the same time, the Earth is rotating underneath, and you get the westward trajectory plume structure, the seed plume. That is the first theory. The second theory, I don't have it here, but I think here is a measurement now. Now we have that measurement, full measurement from low latitude all the way down to the high latitude region. And this is not a model. This is just observation. We just put it together. Here is a geomagnetic equator. And watch that density. It is pushing from here all the way, and it goes to high latitude. And even the second plume, it happens from here, but you don't see it, the base, because this is over the ocean. And to me, this technique makes sense a little bit based on this observation. I was just quietly watching the theory developed and which one is really the real technique that, or a real reason, or the physics behind the formation of the plume. But since up to listen measurement, you can see this huge high density structure is actually going to a high latitude region and forms a plume. Here is one plume again, and then the other plume, it goes to the ocean. And then I get a slice here, but in the slice I included the LEO satellites TEC measurement to see if actually the density is enhanced over the ocean or not. Here is for one. It starts from here at 1830. You get high density at the bottom, and nothing is there. And then 1930, that developed a little bit and pushing to the anomaly region. And then an hour later, the equatorial region is getting empty now. That is just a plume. It's going up and up and up. You get that kind of a structure. This is the sharp density gradient is the one that creates regularity. It's not simple. It's in the scale range from tens of kilometers to down to 100 meter scale.
Well, I think we solved this problem in 2008 with a paper by Joe Hole et al. Wendy Long, who's a significant author, showing that the CMIT model, the coupled magnetosphere thermosphere model, that the magnetosphere electric field, primarily the zonal field, uplifts the plasma and forms these features, which are.
So you agree with this one, or the?
I'm not sure which is which, but the mechanism is the vertical motion of plasma.
Okay.
There's no plasma sphere in the model. There's just magnetospheric currents, which introduce a zonal electric field.
Mm-hmm.
And I think that everybody calls them plumes, but I always feel that that's a misleading term, because a plume implies something that's moving horizontally, like a plume of smoke. And it's really a daytime phenomenon that occurs due to the vertical or a long field line motion of the plasma enhancing the F region.
Okay. Okay. Whatever it is, that's a formation technique that we can agree or disagree. But that's not my objective here. My objective is how this sharp density gradient is forming regularity. That's one thing. And then on my way, that's what I explain how it gets formed. Here's one example here. It's so many DMSP satellites over here. Here is the density over here. Here is the east-west drift. I think that should be kilometer per second, not meter per second. Here is the irregularity that you see along that sharp density gradient, and over the trough region as well. So this is two techniques that you can create instability in that region. One is, of course, the density, sharp density gradient. So you have a density difference and temperature difference. Here you get an instability, get a regularity, the same scale that I showed. The other one is a convection, the plasma convection in the trough region. So if the convection at the trough region is actually, the westward convection is exceeding the threshold value about 0.3 kilometer per second, then you will create instability. And that instability also creates irregularity. And that's why I put the convection speed to see it during on that region. You see the convection is actually greater than 1 kilometer per second, which is way greater than 0.3 meter per second. That's why you get this kind of structures. But is it threatening, which I'll show you later. But the question is this kind of phenomena only the American sector, or you can see it everywhere? Of course, you can see it everywhere. This is one example over the African sector. The base in Africa, this is European sector, but you still see a huge irregularities here. This irregularity, by the way, is ROTI, the rate of change of TEC. But if I have high rated GPS receiver, I can also calculate the S4 index from there. Then it's not only GPS that actually responded to the mid-latitude irregularity. Here is the Ionosphere sitting somewhere in Minnesota area. Here is the E region spread F, and here is the F region spread F. And it's very big spread F structure at mid-latitude region. Here is a Japanese, the Mu Rudder, just looking in the Japan, which is typically maybe mid-latitude region. You can see E region echo, which is very, very strong during not that big storm, actually. It's not that threatening. So you saw the irregularity and how big it is and what is the impact. That's the most important thing. Here is just TEC gradient, the horizontal gradient, changing TEC per kilometer, not per minute. And you can see the irregularity, how high it goes. And then on this side, we put the positioning error on L1 frequency, how it can cause. This is on L1 frequency, and this is millimeter per kilometer. And it's about, it can go up to 0.5 meter per kilometer positioning. That's really huge for landing and taking off. It's just one practice that Nanda Basu put it. This is the precision of the WAS system. I don't know how many of you familiar. The localized performance of the vertical guidance, which I'll show you in a small movie. Here's the availability. If it is available, great 75% and above, it's safe. The plane can use that landing facility. But sometimes it is not available. And you can see KP index when it goes up to 9, sometimes the LPV availability is really way down. And during that time, that's why you get that seed plume structure. That's why you have that huge irregularity. So you see the LPV availability is for, I don't know how many days we have. We have about 600 days, about 2 years time, less than 2 years time. You can see LPV was not available quite significant amounts of days. This is just a cartoon. LPV is just showing you the vertical guidance, whether are you touching the ground or not yet, or something like that. So that is the new facility that was introduced almost a decade ago, and that is depend on the mid-latitude irregularity structure, whether it will be available to operation or not. And yes, we do have to worry. That's why our team gets selected to address this kind of problem. But when it comes to the low latitude, everything is different. The geometry is different, and the geomagnetic field orientation is different, and the physics is also different. And the low latitude irregularities, actually, it can operate by itself without any input from the magnetosphere, because it's a closed field line, but there is input from other source, which is forcing from. So this is the related instability, or the growth rate equation. Everybody is familiar with it. So the electric field, and then the density gradient, and also the collision frequency. And those parts are more dominant, especially the electric field. That's what we believe. But I'll show you if actually this, the vertical drift or the electric field is actually the dominant part. Here is a modular. The modular tries to model, look how the seeding look like. It's very small structure, and then it develops very quickly. You can see this kind of structure even during quiet time. And that's why without any input from the magnetosphere, you can have bubble or scintillation or irregularities at low latitude very easily. So our objective is not to address the physics. Our objective is why it is different from one longitude to another longitude. But the magnitude, everything is different, which I'll show you. And then we have observation, different kind of observation. We put a lot of instrument. We put GPS, high-rated GPS receiver or regular GPS receiver. We have also VHF receiver, about 250 megahertz, and it's just linking geostationary satellite in different direction, one to the east, to the other, to the west. And then if the irregularity is just coming into your link direction, then that's how you get this irregularity measurement, or S4 index in other way. So the top one is from the VHF measurement. The middle one is from high-rated GPS receiver that calculates the S4 index. The bottom one is from regular GPS receiver, 30-second or 1 second or 10-second resolution. But you can calculate rate of change of TEC, and that is a proxy for S4 index. So if I don't have these two instruments and have regular GPS receiver, that's okay. I can monitor the scintillation activity at a given location. Another way is from the regular GPS receiver, and instead of ROTI, you have this GPS TEC. The blue one is the GPS TEC. The green is the elevation, which is the same scale over here. Here's a positioning error that I showed you before. And what happened here is you can see the TEC is, going up and down, and we believe that is due to the bubble. And then if you calculate the depth of the bubble from the trough to the crest region, then you can tell how big it is, the magnitude of that bubble. And this is what it is. This is the TEC, the depth from the trough to crest region, and as a function of time, you can see from the solar minimum, when you come to solar maximum, that depth is getting stronger and stronger. That is telling you that the scintillation activity during that time is very high. So another one is a GPS receiver you have. The GPS receiver on the satellite, a LEO satellite, looking upward, and you think anything above swarm satellite is really quiet, so I don't see anything. So swarm has also in situ density measurement. Here is swarm A and B. They were flying around 460 kilometers. And here is the irregularity when it is crossed the eastern part of Brazil over there. And then at the same time, you have the GPS looking upward. So we apply rate of change of TEC on that, if really the bubbles actually penetrate all the way down here. Here is what we get. And then we just plot it as a function of time. Here is ROTI as a function of time. And then the TEC is the red and the green from the two satellites. And then if you don't trust us, then we put the elevation angle. So it's actually high elevation angle, nearly vertical. And you get the ROTI is actually very strong. Did I see that kind of stuff on the ground? So we have GPS receiver around that point. And then that GPS receiver actually not only accepting signal from GPS constellation, it can also accept from GLONASS. Here is a GLONASS down here. Here is a GPS ROTI as a function of time. And the dash line here, the 2 dash line, that's the time slot where swarm is passing over it. So you can see during that time, you get that kind of regularity structure. I also have another one, which include actually swarm B, which is a little bit higher altitude. And you can see how big is the scintillation or the irregularity above 500 kilometers. So if you combine all these different instruments from the ground, from different altitude of the LEO satellite, you can tell how far the scintillation or irregularity penetrates all the way down to high altitude, sorry. So the modulars, since there is a lot of modeling here is the modeling part, how they try to capture this S4 index. This is the VHF. As I said, they are linking to you have VHF receiver here. One is looking to the east and the other one is looking to the west, because they are tracking 2 different flights of the geostationary. And this one is east link and this one is west link, and I think it is in Cuba. And then the red one is a model from the PB mod, John Retterer. You can see sometimes the basic parameter for scintillation for the modelers is to capture 3 things. One is onset time, and the other one is the amplitude, and the third one is the duration. If you capture that, problem solved. But sometimes you can see this red is a model. There is a few minutes delay between onset time of the model and onset time of the measurement. And then in the west link, more or less the same. Here is ROTI at the same location at Cuba. And you can see the ROTI also start a little bit earlier than the model start. Another location, sometimes in one link, it perfectly fits and it's really captured very well. But on the other side, doesn't matter. I mean, it is off, obviously. Well, that's okay, because if you are watching in the west link and you capture the onset time, but you didn't on the eastern side because the bubble might be moving from one side to another, that may be the reason. But it's doing actually great compared to the others. And we did also try to look at from one longitude to another longitude how the model is performing. Still, we are in the American sector from east to west. I put the longitude here, 78 or 79, which is a Hicamarca, and then about in Brazil and way eastern side of Brazil. You can see in the Brazilian, in the west coast of the American sector, the onset time with ROTI is really reasonably good. They capture very well. The duration is a little bit off, but somewhere in Brazil, totally get off. They capture the onset. The magnitude is also okay, but the duration is totally off. And then here is another one in the east, and it's not capturing very well. Bill?
Can you say what goes into this model that allows
It's a physics-based model.
What's that?
It's a physics-based model.
Yeah, but I mean, what is it using?
He used the A cross B drifts. I think he used the background density is, I think, IRI model. And then the drift is Sherrill and Fair's vertical drift model. But for this part, I guess, that's the model he used. I thought he used CNOVs, but it was 2004, so he didn't. So he used just a model to drive, but it is physics-based model. It's not empirical. But he does very well. At least this is the first time we saw at least S4 index 1-to-1 correlation comparison. That paper might be out very soon.
Thank you.
So we have the measurement, the modeling is doing good, and let's see the statistics. here is the statistics for the longitudinal variability. All of them are the VHF receiver that are 250 megahertz, that the Air Force puts a bunch of receiver around the globe and then just drop it like a ball. We don't have funding to keep it, but some of the instruments are still providing data. We get data from them. We are trying to get more money to reinstate the CINDA project. This is forcing that. So this is a local time from sunset all the way down in the morning. And then the horizontal is day of the year, or I put in months. Different panel is different longitude. For instance, this panel is for Christmas Island over here. This one is in Ancon, and that one is Kiowa here, and then to continue all the way down up to Kwajalein. Kwajalein is down there. So you can see clear seasonal variability, which is obvious. Equinox is maximum, and then June solstice. In the American sector, you don't have it, but in the African Asian sector, you still have it. That's another issue that the model is not functioning. It is functioning very well statistically in the American sector. When you take it out of the American sector, it gets off, especially the June solstice. I believe there is no bubble, but there is another sector. So here is from the GPS receiver, from one of the techniques that I showed you, the same station, the same location, just to compare these two. And you can see even GPS also in the Asian and the African sector, the June solstice is actually significant bubbles you can calculate. There is another way that I brought this one, which I'll show you later. It is CNOVs from irregularity measurement. This is day of the year. Now this is a longitude. And this black curve is the time and location where the terminator, the dark side terminator, and then the field lines are parallel. And that's where both field lines are on the night side. That's where you get more bubbles or irregularity structures. This is new. This is what I showed you earlier from the ROTI, but looking upward from different satellites. This is the top side irregularity structure, in short. And you can see all the oceans and the lands, everything is covered. But the structure is more or less similar to what you observe from the ground base. Here is from the GPS receiver, and that is also the TEC depths that I showed you, the bubble depths. They both shows you the same structure over here. Significant structure in the African sector, and during June solstice and Asian a little bit. And other satellites also observed it before. And this is my topic. This is the modular. The modulars, statistically, they did very well. They capture all these statistical structures very well. But the day-to-day variability is an issue, and like the one that I showed you earlier. Now, the question is, what is the reason that we have this kind of structure around the globe? We know the magnetic field structure is weird, and it's off and on. And you may wonder, it is obvious, the electrodynamics is a problem. But there are several electrodynamics components. So which one? Is it the drift, or is it neutral wind, or is it the conductivity difference from one longitude to another, or is it a localized gravity wave, or is it the global tide control this longitudinal variability? That is the one that we are trying to address. Go back to this plot. This is the one, the top side. This is from ROTI. This is from TC depths. This is the drift from CNOVs. And we did a lot of discrimination on CNOVs. We took only when the satellite is within plus or minus 8 degrees geomagnetic. And we ignore anything when the satellite is above 500 kilometers. And we remove negative or downward drift. This is only the upward, because the upward drift is the one which is responsible for regularity. That's what we believe. Now you can tell the one-to-one comparison between the bubble distribution and the drift. Just forget this one just for a while and watch here. Here is huge irregularity, both GPS or VHF, everything. But we don't have drifts, upward drift during that time. Almost none in the African sector and then everywhere. Some people, they model the drift. This is the best model that I saw so far because it shows the day-to-day variability at least. And they capture everything very nicely. And they have also downward drift over here because that's what white, because I removed it. But in the African sector, Halu, he got something, but CNOS didn't see any stuff. But this is not 1 year or 2 years or something. It's many years of data. So if not the drift, then what is controlling this structure? Well, of course, CNOS also show the same structure here. Shaosong did, okay, just to correlate the occurrence of the bubble as a function of PRE. That's pre-reversal enhancement. And he did it in different seasons. This is February, this just the winter, and then June solstice, and those two are equinox. And at the bottom is a vertical drift, PRE, the maximum. And there's no good correlation at all. He divided into different solar flux. If it is really dependent on solar cycle. So this is when F10.7 is less than 100 on top one. So June solstice, December solstice, equinox, you can tell. There's no one-to-one correlation. It's supposed to go that direction. But the equinox is a little bit better than June and December solstice in terms of the correlation. And then here is again at different F10.7. So there is no, the drift is not always the reason for the irregularity or kicking the irregularity enhancement or something. That means there is some other thing that we need to worry about. So you see that the drift is not actually the only driver for the irregularity, at least at different longitude. So we try to add, yes, Lahan.
So the previous figure, so this data are from local station measurement or?
This is from CNOS, I'm sorry. Yeah, this is from CNOS. CNOS has an in-situ measurement at the same time as the drift measurement. So he tried to balance because it measures at the same location.
And does CNOS kind of more represent solar minimum conditions, or is?
Well, that's why I think the maximum he has is 100, 140. That's about 2013, 2014. Didn't have that much because CNOS lifetime was 2007 to 2015, and actually died in Ethiopia, unfortunately. So we try to look at the wind, and if there is a wind magnitude difference from one longitude sector to another longitude sector. This is in South America, Brazil. The geomagnetic is about 6 degrees. This is actually November, December, and I can't see it here. And then January, February, March, April. So different color is different year, the yearly average. And then the black curve is one model, the wind model. The magnitude is very plus or minus 50 meters per second. So we were dying to get the wind measurement in the forgotten continent, Africa. So John Meriwether, Jonathan McKellar, and myself, we got some support from FOSR, and we put one in Ethiopia. And I know Sean also put in Nigeria, and he's trying to put in the West African sector as well. So this is on the northern hemisphere. This is in the southern hemisphere. That's why the direction is flipped. Instead of going up, it goes down here. So that's not a problem. This is a meridional wind. And they divide it into two, northward looking and southward looking but different year. And the green one is one model. So I don't think the magnitude that varies from one year to another year. So from 2012 to 2016, I don't see that big difference, I think. Because I just wanted to warn you, they're not the same year measurement. But the magnitude is no big change between the American sector and then the African sector. They both are within the same, it's not that big difference between the two sectors. Whereas working now, we have a student to do the same year time measurement. Now we have, since 2015, we have measurement from Ethiopian side, and then we have measurement in Nigeria, the mid-African sector. So we try to combine that one. At least we are working with the Ethiopian and Brazilian sector now. We'll include Nigeria and see if there is a big difference. But at this stage, from this, actually was not happy when I see the data. Wow, there is no big difference. So what is going on there? So here is neutral wind, the zonal neutral wind again. Its the magnitude is still the same between American and African sector. But again, this is different year measurement, but we are working on to get the same year measurement. So we saw the drift, we saw the wind, we get disappointed, and now we move to another one. So forcing from below. And that would be another issue. So I have some, because all of you knows this one, the gravity wave, which can be generated by so many factors, and it can penetrate all the way down to the ionosphere and see the bottom side, and that grows to the bubbles. And this is just one of the movie that was generated by one of our former student, a PhD student. And what you see here is the tsunami structure from Japan earthquake, and the blue is a sea surface anomaly, and top of that is a TEC irregularity that shows you a gravity wave, how it is propagating west. So we try to address, but we don't want to involve modeling here. We just wanted to do from measurement. That's my objective, at least. So we got a technique that I think has been already matured. And we went to the satellite measurements from time, and that's SABR, the temperature profile. So from the temperature profile, you can extract the gravity wave structure. Here is the altitude, and this is, I think, latitude that I put. This is just a gravity wave structure, but this one is just the amplitude. At different longitude, here is the African, American, and the Asian sector. And to see if actually they have, this is just ongoing, it's not yet developed very well. But we see not that big, but clear, not the same magnitude you can see. I mean, there is a difference, slight difference, but we need to do more statistics. And then at the same time, we went back to the TEC, the ground-based TEC, and tried to calculate the TID structures. And we actually noticed that during those times when we have these gravity wave structures, the TIDs, instead of equatorward, we got poleward propagating TID structure in both, here is the American sector, African sector, and Asian sector, but with different magnitude. The amplitude of the TID is actually not the same. So that is encouraging, then we are pushing to that side direction. So, and then the gravity wave that I showed you is actually generated on this tropical region, and that tropical region was actually co-located with this intertropical convergence zone, ITCZ. And it varies from one longitude, one latitude to another latitude and everything. So I was wondering to see just measurement, not modeling again, because the ICTZ is just a merging between the two winds at some location. But it varies from one season to another. But I wanted to see we have those bubbles all the time active. And if that ICTZ location, it actually moved from one point to another. And this is thanks to Helene. I contact NOAA people to get this data. And this is what I got. This is actually not 1 year or 2 years, many, many years of data. And then plot the ICTZ location. And the black line is the geomagnetic equator. And in the African sector, it's funny. It doesn't move that much. So it's all the time up there. That tells me something, maybe for the modulars. That means if ICTZ location is right around that area, then you probably have gravity wave all the time there. And then that gravity wave probably seeding the low latitude irregularities. Probably that's just a suggestion now. And then we move to the global scale of the non-migrating tides. You can see this 4-cell structure. Again, it's not modeling. From that temperature, the server temperature, that's what we extracted it out. And you can see this kind of funny structures, 4-cell structures, very nicely. What does it do? It can actually modulate your neutral wind like this. This is a measurement, and that with neutral wind modulate the density up in the ionosphere. And this is from the satellite, the CHAMP satellite, and this is from the ground-based GPS DEC. And this is a famous paper from Thomas Emil that image FUV data looking at the brightness of OH emission. And this structure at 4-cell structure here, that you may say, okay, we have a strong drift velocity. That's why you have big widening up. That leads to the birth of amber. This is why amber come into the radar. And I think we celebrated 10 years since we operate this. And this is, the idea is just to identify the longitudinal structure of the electric field or drift, whatever you want. So we measure the Electrode Yet, which is electric field in other words. And it's only the day side. And the one that I showed you is only day side phenomena, the large scale structure. And here is how we calculate the Electrode Yet. We put the magnetometer in the same meridian nearly, one at the equator, another is off the equator, and then they measure current. We don't care about the amplitude of the magnetometer values because we subtract out. So this magnetometer, for instance, the one which is located off the equator, it measures the main field, it measures the SQ current and field line current, even if it is weak, and the ring current, you think it is weak, but during shock, it is actually big. And then the magnetopause current also there during the storm. And then the one at the equator, it measures everything what I said, plus the Electrode Yet component. However, this, the one at off the equator magnetometer, it should not be more than plus or minus 9 degrees. If you go out, then these currents may not be the same as the one that you measure at the equator, and then you ended up maybe wrong Electrode Yet component. So if you take the difference between the two, like what I did here, the red is at the equator, the green is off the equator, and then the black is the difference between the two. That black component is the Electrode Yet. So you can, the Electrode Yet means just electric field. You can convert it to electric field if you want, with a very simple calculation. Then apply a neural network technique and translate that Electrode Yet into vertical drift and compare it with radar measurement in the American sector. And the other sector, we actually depend on the satellite measurement. And here is this is from the magnetometer, here is from the radar, and the agreement is really very well. So from now on, I'm going to talk about only the black curve, which is the Electrode Yet component. That's what matters from one longitude to another longitude. Because you may wonder, okay, we may disagree with a neural network when we translate it to vertical drift, but we may not disagree with the Electrode Yet component because it's direct measurement. So we did try to see from one longitude to another longitude, because many, many years ago, I had the story. Whatever Hikamarka show, drifts or whatever. It is the same everywhere. That's what people believed. And then the satellite comes, and then the satellite shows different story. And then scientists wake up, and then, okay, this is not different. So this is different color, it's different longitude. And then the one, this is just, that should be, okay, I put the X-row speed drift component here. But anyway, that's fine. So different color is different longitude. This is American sector, and that one is the Asian sector, way in Philippines. And then it continues, the American and then the African sector. The idea what I wanted to make over here is the drift is actually not even close. They vary from one place to another. It's one day, but here is the statistics. Here is a network that I put the pair. Start from that pair is the top one. The next pair is this one. The next pair is that one. And it continues all the way down to Philippines. That's the Philippines, and that's Thailand. You can see the Americans and the Thailand and the Philippine, the Asian sector. The drift is so crazy high. Of course, you can see a huge seasonal variability. This is the Electrode Yet as a function of day of the year. This is for the first time from the ground that we demonstrate that the electric field is actually not constant everywhere. It varies. But sometimes, the funny thing, if you pay attention very closely, the across speed drift or the vertical drift and the bubble distribution, sometimes they go opposites. The bubble is stronger in the African sector sometimes, maybe most of the time, but you can see the drift or the electric field, even if it is day side. But the night side, I'll show you in a minute, is also the same as the day side. Is stronger in the American and the Asian sector. Here is SINOFs. This is statistics. The same thing that we did some discrimination here. And different color is different longitude. So this is, the red is American sector, and it goes all the way down to Asian sector. So what we did is, if we are watching for the satellite to come at this meridian, and then we just expand it up to plus or minus 3.5 degree longitude, and then we just dump everything there, and then average it, and that's how it is. So even the pre-reversal enhancement, if you pay very close attention, you can tell that the American sector is stronger than the African sector, but the bubble is the other way around. This most of the time you can see, not all of the time. And another thing we did is just to see if this Electrode Yet or the electric field, another way. So Hikamarka, it gives you the vertical profile of the drift or the electric field, whatever. You can convert that one. And I know Bella Fiera has a paper. It shows the across speed drift is not really the same as a function of altitude. So many, many years ago, before most of us was born, this is in 1967 equinox, there was a bunch of POGO satellites, and the mission is to identify the Electrode Yet as a function of altitude. And here is the Electrode Yet. This is the Electrode Yet as a function of altitude. And the Electrode Yet was just like that's what they showed during that observation. And the maximum is around that region, which is obvious. And then it goes down and it goes up. I don't know why it goes up. So now we have two satellites orbiting. One is around that region, and the other one is around that region, and they carry magnetometer. So using from that magnetometer, you can extract Electrode Yets globally. So here is the swarm satellite. Swarm B has 500, and we took only 1 hour slot from 10:30 to 11:30. And then the same is for swarm A. And this is what we got. We got the swarm A, which is around that area. You see really stronger Electrode Yet component here. But if we go higher, that's really weak. And this is negative. You know why negative? Because the satellite is orbiting above the Electrode Yet region, and that Electrode Yet produce induced magnetic field, which is opposite to the geomagnetic field. But if it is below, it should be positive. but we didn't convert it into Electrode Yet current, which can be done. So you can see the Electrode Yet is actually not uniform altitudinal-wise as well.
Yes, I'm kind of lost. So for the left, for the right pictures, you assume that you basically have the current flowing below the satellite, while on the left, the satellite seems to be in the current region, so you would have to assume.
Oh, the left is, okay, the left is not my observation. It's a long time ago, somebody measured and showed this, the altitude profile of the Electrode Yet. And we tried to reproduce that in the current measurement. And this is, our satellite is at that altitude. And then at that altitude, here is the Electrode Yet component we got. But the other satellite is around that altitude, and which is really stronger than the higher altitude. And this is the same thing what they observed many, many years ago. But this, the left one, is not our data. Did I answer your question or not?
Kind of, but you assume the current is flowing below the satellite, of course, on the right.
Well, the Electrode Yet is actually below the satellite.
Yeah.
Okay. The Electrode Yet is below the satellite, but you can sense it even higher altitude. That's what. Another stuff that we looked at is just an addition. Is Lunar Tide. We ignored it, but we tried to everything possible to understand the longitudinal variability. And we took 4 long-term measurements of the magnetometer. This is Hankayo, and this is Mount Barrow, which is west tip of Africa. And here is eastern side of Africa in Addis Ababa. And this one is jump on Davao. Davao is in Philippines. And this is different season. We have December to February, this part here. And the middle one is March to May, and June solstice, and September. You can see clear seasonal variability and also clear longitudinal variability. It's in the American sector, it's stronger, but the African sector is weaker. And then in the Asian sector is a huge amplitude variability. I think last week or a week ago, Larissa showed us that actually Lunar Tide actually creates a huge impact on STSW and the other TEC stuff. But we haven't looked at how big impact this one it creates on one-to-one. Just to show you everything is, it also has the solar cycle variability. This is 19 to 2000 solar maximum, solar declining phase, solar minimum, and solar maximum. You can see a very huge structure, even a Lunar Tide. So everything has to be included to understand the physics. That's my point. So the upcoming mission is very exciting if it gets launched. This is ICON. They have MIGHTY, they have IVM, and they have FUV. The MIGHTY, you can get gravity wave because they measure temperature profile. IVM, you can measure drift or upward. And then the FUV, you can get this kind of brightness, and you can understand the physics really one-to-one. I don't know if it has in situ, but I believe they don't have in situ measurement, right? The in situ density, just to see a regularity. IVM. Oh yeah, IVM, sorry. IVM has also in situ. That is so you can measure regularity, drift, and gravity wave, and then FUV. That would be exciting to understand. So ICON is actually a mission to address this forcing from below, which is really very nice. And then gold, you have this ONH2 ratio image satellites. I think it was image, yeah. Many years ago, they have this bite out in the Australian sector, or the OE mission. And then we got GPS receiver, also none, no TEC at all, and we were worried. And then Mark, he went to Berkeley to give some seminar talk, and he saw Thomas email us a slide, and then And then the topics also the same thing. So you can see one-to-one correlation to see. And then especially if bite out, does irregularity suppressed or really enhanced, or maybe for GPS it is weak. If the background density is weak for GPS, even if there is irregularity, it doesn't matter, it penetrates. But for VHF, still worried. So just combining all this stuff would be exciting to understand. Another mission which is coming up is GDC, the Geospace Dynamic Constellation. They are planning to put 6 of them and 6 different orbits. It doesn't have any PI like Icon or something, so anybody can put an instrument, I guess. That's what they said. But it addresses a lot of stuff. A lot of physics it can address, even the seed plume, like forcing from above. There could be OH2 emission, the gravity wave, and the wind modulation, and then the current circulation at different altitude. It's very exciting. But here is what I wanted to do if GDC become materialized and if they allow me to put GPS receiver on. If you put GDC carries a GNSS receiver, not GPS, GNSS, it accepts many of the constellation. I'll show you the constellation. So many constellation now. You don't pay anything, a dime. Of course, somebody has to pay it. It is GPS, GLONASS, Galileo, Bindau, Kuzi, and then forgot the name. IRNSS. They have already launched 6 of them, but they're not public. But last week, a week ago, we were in India. I saw IRN's measurement, the first measurement, the scintillation monitor, that they have really nice stuff. So GPS has 31 satellites of them. Galileo, GLONASS 24, Galileo 13. They said 13. The one that is functioning is less than that right now. Bindau, they have 15, but it's regional. You cannot see it in America or somewhere. Kuzi also, they have 4. And so if I have GPS receiver sitting on a satellite, assume this is just one of the LEO satellites, the GDC, you can call it. So it's just passing to that direction. And then accept signals from there. And try to image the vertical structure of the ionosphere and the plasmasphere from wherever the satellite altitude is up to the GPS satellite. And then you can put even as fine structure as possible if you want, because you get more ray paths. So if the satellite only carries GPS receiver within a certain time period, about 30 minutes, this is the ray path that you get. And if it accepts GLONASS, this is what you get. It covers part of it. If it accepts Galileo, it covers everything here. This is what I can see in this region and this region. But if the satellite goes to that direction, this is what you get. Because when you pass over that region, now you'll be able to see from Bindau, Kuzi, and I didn't include from the Indian satellites. So look, this gigantic ray path within 30 minutes. And I can actually capture irregularity if I get all these kind of structures, how far it can penetrate all the way down. This is very exciting, but I'm not sure if they have decided to put GPS receiver on board or not. So that's structure from cosmic satellite we did a few years ago. So this is just my summary. Of course, you saw the multi-instrument measurement shows you ionospheric structure, both mid-latitude and low latitude. They're not uniform. It varies from one point to another point, and the drift is not the only drivers, even if it varies from one longitude to another. And this is what we are diving on, and I'm glad I came here because many of you are working on that topic, and it would be nice to collaborate modulars and the measurement, and then the ITCZ location would be nice to be included in the modeling part. Do I have a minute? 1 minute? Okay. So I have other topic, which is shifting to outreach. Now, when you operate an instrument, you have to do some diplomacy. And that diplomacy is through outreach program. So we start in 2007, and the person who was the backbone of all this mission is Tim Follerar. He's here. I'm glad you are here. And we started over here in 2007. And I remember when we talked to some of the people over there to host our instrument, and they said, "Oh, what do I have to get? What is my benefit?" Because some of them, they never heard about space science before. And then we continue. We had several. The second one was this one in IHY, and things is getting better because they understand something. And now they start asking us to give them an instrument instead of begging them to host our instrument. So it totally shifted. So it's not only the African sector the African region we have been doing. Initially, we start from there, but now it has grown up. And we get noticed by leaders in Africa. And then 2015 or 14, the Rwandan government formally invited us to host one of the summer school in their country, and we did. It was nice. I don't know how many of you watch Hotel Rwanda. That was the hotel they gave us to host the conference. That was exciting. And then we went several things. And this one, the Boston College and the ICTP, they made a formal MOU agreement. So to have a series of workshops, initially for the African, targeting African. Now it grows and it becomes global. We get students from Asia, South America, Eastern Europe, everything. And they celebrate the 10 years, non-stop, every year. And we went not only there, we went as far as to Indonesia to get, and in Indonesia, I was so surprised. So many women to see on space science. But the bad thing is, in the daytime, they were active and participating, and then in the night side, they go to their babies to take care of. And it was very nice. And then India and of course. And then we get noticed by the big guys, like AGU. And then AGU decide to have the first Chapman conference in African continent, the space science part. And we have it there. Tim was the leader, and we participated. Another huge international conference we get noticed and try to host it there was an ICEA meeting in 2000. We actually compete with Brazil. And when we present in Paracas in Peru, 2012, and the Brazilians say, "Oh, we have this city, we have this facility, we have this." And I told them, we don't have that. But the space science is booming in Africa. If you wanted to participate and just contribute, please have it there. And then thanks to them, they voted for us instead of Brazil. And we host ICEA there for the second time in Africa, actually. They had it one in 1971 in Nigeria. Now you may ask, what is the impact? I'll show you the impact. This is the impact. For instance, this one. This is a publication rate. This is year as a function of number of publication. And you can see the publication rate from the African sector during that time was very, very low. And this is where ICTP and Boston College get married. And they sign this MOU. Look how it get jumped, the publication rate, everything. And then the production, just brain drain to stop it. So some of them, they are very smart enough. They introduce the curriculum into their university, and they don't have expert to supervise student, but they become a fake supervisor, but look real supervisor from overseas, and co-supervise with the student, and they actually become productive. This is one of my students. He was actually honored by AGU last year, and he got his PhD, the first PhD in space science in Ethiopia. And here is in Kenya, the first PhD in Kenya in space science. And the others, which I don't have it, they have in Cameroon, they just graduate Algeria, and then Chile. You can count many of them. And then we actually just put some legacy for all these activists, and we produced that book again. With Tim was the lead, and I was following. Another one is a special issue we have was Analysis Geophysica that we produced. So as I said, we started in 2007, and this is what that continent has an instrument during that time. None. A few magnetometers by Intermagnet or USGS, and then a few GPS receiver by Tectonic Group. That was all. And this is in 2015. But I mean, I know a lot of instrument has been deployed after that. And this is what we have in 2015. It's not only GPS, not only magnetometer. Now you can see even optical instruments, radars, and ionosones are there. And here is a 50 megahertz backscatter coherent scattering radar deployed in 2014, the first in kind in the African continent, and it's now operating in Bahir Dar, Ethiopia, right there. And then think big. We thought big, and we were up close to get it, and then NSF messed up, so didn't get it. So this one was to get a MISR radar in that continent, wherever, I don't know. But we were planning to put it in Ethiopia, and that was the first time to bring the politician and the scientist in one room. And this guy is the Ethiopian ambassador in the United States, in Washington. We invited him to come, and those are the the scientists from different places we invited, and to put this radar. And then he promised to provide land, all these structures, but we were only to get from NSF these panels from there. And then all of a sudden, NSF comes upside down, but I still didn't give up. Still, when NSF becomes stable, I'll push it hard again. Thank you. We're asking questions.
So your conclusion about the longitude dependence, that you've got your sort of a climatology of where they're occurring that comes presumably just from the climatology of the vertical plasma drift, but then the day-to-day variability is superimposed on that from other wave sources. Is that your conclusion, or is it a variability in that vertical plasma drift that is? Do you need anything other than the vertical plasma drift, or do you need another component, say like asymmetry in the winds or something else? Do you have a sort of a bottom line of what you think?
Well, it's everything, a little from everything. So we saw the drift is not only driver. It's not the only. It's not actually the one that controls the longitudinal variability. That's for sure. From the measurement that we saw, and the wind measurement, we are still doing it to do it at the same time, the same year, the same measurement from different longitudinal sector. That is also doesn't look like right, but it's okay. But right now, I think the one it is controlling is the seeding from the bottom. But the question is, again, I try to show day to day, and then just the statistics, how the gravity wave is a gravity wave different from one longitude to another thing? Is it stronger here and weaker here? It depends. If the gravity wave is stronger, you see it strongly, and then you get strong bubbles. That's what we are working right now. But I encourage you guys, the modeler, to tell me if you model the gravity wave, is actually the gravity wave amplitude the same here and there? If not, what is the reason? And then I think right now, my understanding is not the drift only factor or the wind. I think it's forcing from the bottom, the localized gravity waves is localized stuff. And that could be the reason that answers the longitudinal variability. Yeah.
gravity waves are not the only form of forcing from the lower atmosphere.
Yeah.
The dominant thing that affects the thermosphere, and particularly the electro jet, is tidal forcing and other large-scale waves.
Tidal is global. And I wanted to see localized from one point to another.
Well,
That's what.
The combination of migrating and non-migrating tides
Yeah.
and significant longitudinal variability is shown in those.
The one in my results, the migrating tide is removed from the two because the satellite has 12-hour difference, and if you take the difference between the two at the same location, same latitude, then you can remove barely the migrating tide.
Okay, but
Yeah.
the central question about the formation of irregularities, I think, is since it's clear that vertical drifts are implicated, and it's clear that vertical drifts vary with response to geomagnetic activity, but especially in response to tidal variability, both day-to-day variation of the tides and also the structure of the geographic distribution of tides with the interaction of the various components. So from that, you will get variability of the vertical drifts and hence variability of irregularity. But the question is, do you need, in addition to that, some sort of seeding mechanism that's an additional variable that accounts for the day-to-day variability? You can explain a lot of the climatology and the longitudinal solar time dependence from the known processes, which are possible to model with global models. Small-scale structures are more difficult to both model or observe, and so I think that's still a very open question.
Mm-hmm.
The degree in which the gravity waves are implicated. And, the gravity wave people say, "Oh, absolutely, need gravity waves, otherwise nothing happens." The large-scale and global perspective is perhaps more skeptical of that point of view, but I think it's an open question.
Yeah. I agree with you. The additional seeding mechanism is zero. So is it a gravity wave or something else? I agree.
Where is that radar?
In Ethiopia, Boulder, where you were for ICA meeting. You didn't go and see it?
No, I didn't go.
A group of people, they went down and to see it. Yeah, it was there when we were there.
Where is EMI one right now?
What?
EMI.
Oh, the Amida. I think it's high latitude, and one is in Alaska, I guess. Poker Flat is Alaska, right? Yeah, Resolute Bay. And they have 14 panel in Hikamarka. Just coherent mode, not incoherent. But our target is to get incoherent mode in Africa. Yes.
So you mentioned that Africa has some particularly high currents almost throughout the year. But if you look at the statistics throughout the year, are they pretty much uniform, or they also have a seasonal?
They have seasonal.
They have
yes, they have seasonal. Okay. They have seasonal variability as well. Bill, you have a question? Okay.